Welcome back. I hope you enjoyed a nice lunch, and I hope you enjoyed the discussions and the networking sessions before lunch, and maybe that you got a chance to try this 3-minute quick or speed networking tool again. We are moving into the second half of the day, and I hope you feel ready for that. And in the second half of the day, we have 2 focused sessions. First, one on vehicle-to-grid and smart charging, and then we have one on wireless charging solutions. And then we have yet another round of really interesting hosted networking sessions. And finally, wrapping up with some reflections together with our moderators. So without further ado, actually, I'm going to hand over to Neale Ryan, Senior Program Manager, Automotive at Innovate UK, who will moderate the session about vehicle-to-grid and smart charging. Welcome, Neale.
Yeah, thanks, Johanna. Yeah, good afternoon, everybody. Welcome back. As Johanna says, I hope you either had a restful lunch and you're recharged for this afternoon, or if you were networking in the networking sessions, I hope that was productive for you. So, good afternoon and welcome back. I'm delighted to be joined by so many delegates from both UK, Norway and Sweden. We hope you're finding today to be extremely useful and productive. So as you've heard, my name's Neale Ryan. I'm a Senior Program Manager at Innovate UK. You heard from my colleague Josie Wardle earlier on this morning. We both work in our transport team. So as Josie quickly mentioned, Innovate UK funds a range of transport-related innovation programmes supporting business-led innovation across road, rail and maritime activities. Mostly that's focused on the transition to net zero, and obviously EV charging and electric vehicle infrastructure is at the heart of what we're doing. Focused on this afternoon's topic of vehicle to grid, I've been involved in the UK's vehicle to grid programme since we started it in 2018. So it's an area that I'm very interested in and passionate about, but I'm still learning all the time. So I hope to learn something new this afternoon as well. So what's our session focused on? Well, as we've already heard this morning, actually, to electrify the transport sector quickly enough to meet our climate goals, EV charging infrastructure needs to be coordinated with our national power networks and grids. Aspects such as available grid capacity and the level of renewable power production need to be considered. We've already talked about these issues earlier on today. So how can ever-growing numbers of electric vehicles support or manage grid capacity issues and or provide grid services? So we've got 4 fantastic speakers with us this afternoon. The topics, or the sorts of topics we'll cover, include what are the technical challenges of the vehicle-to-grid solutions? How do you create a compelling commercial offer for consumers around vehicle-to-grid and flexibility? And what will the future look like? So in terms of our speakers, first up, first up we've got Åsmund from a company called Current, based in Norway. He's commercial director and founder. Current is a technology company providing customers with a vendor-independent charge point management system, and has been part of implementing Norway's first vehicle-to-grid installation. So welcome to the virtual stage, Åsmund. I'll hand over to you. Thank you.
Thank you very much. I'm not sure if you can see my screen yet. That would be helpful if somebody... Yes, there you are. So hi, I'm Åsmund. I'm from Current, and we deliver software for EV charging stations, and I'm here to talk about vehicle-to-grid. So first of all, what we do. We have a charge point management system that has 4 modules: operation management, billing management, tools for the EV driver, and energy management, that we can supply to any charge point operators out there. And it's already certified with approximately 40 different types of hardware that is OCPP compliant, which helps our businesses go to market fast, great customer experience, and actually reducing the cost of ownership and increases the revenue. And this is a bit important because we've been doing this with smart charging since 2017. So first of all, I'll just briefly discuss something about what we've done in Norway with vehicle to grid. So some of you guys already know that there are technology available in the market, both on the vehicle side and from the charger side, to actually implement vehicle to grid. There are lots of constraints, both regulatory and technical, but it's feasible to do so. And in November 2019, we used a Nissan Leaf to actually power up the whole campus of Evenstad in the middle of Norway with Statsbygg and Nissan, and show that the potential of the distributed energy resources that the EV are, and how that could be implemented in an area with a low capacity in grid. So to put this into perspective, vehicle to grid needs to cover the whole value chain, from production to the actual EV and everything behind. In this presentation, I'll mostly talk about the application behind the meter, but there's lots of interesting opportunities in front of meter. For example, flexibility, congestion management, and so forth. But to be able to do that, you need to be able to control what's behind the meter, and that's what I'm going to focus about here. So, to start, to be able to do vehicle to grid, you need to actually understand what kind of vehicle and what type of customer do you actually serve. So, do you just do employee charging at a school? You probably don't have the right type of vehicles or equipment to do it properly today. Whilst if you do it with like a bus or a heavy commercial vehicle, you would have high-speed and DC chargers and big enough batteries that you probably could combine and get something out of it. So this slide just tells you that you need to actually understand the needs of the customer and the people using the charger before you start implementing the vehicle to grid part, because that is just transferring energy to or from a battery. So what we do in our cases, we display and monitor the actual energy usage in real time. So I was talking about the constraints. So we have like a static load management system that ensures that there are not going more or less energy towards the facility than it actually can do. Then we can, by smart charging, divide the capacity towards the different types of user according to their needs, either by adjusting the power or adjusting the time in the queues or when they're going to charge. This is basically a basic smart charging, which could be used in most cases for most chargers. Then at least in Norway, the most important part is the peak power control, because most facilities will pay a peak tariff that is just killing the business. So it's all about reducing the peaks and getting the most flat type of usage. To do that, we see that vehicle to grid is a huge part of the solution. If you have a large fleet that is doing what fleets normally does, or at least cars usually does, standing still, we have a huge potential in actually saving energy and distribute it in a better way. So with vehicle to grid, we could first of all change the energy flow between the vehicles and then utilize the capacity to either help the facility reduces the cost or to help operating and serving the needs of the grid on the higher stage. So here I have a picture from Norway. This is an average household in Norway with an average EV charging at average time. On the left-hand side, it's done without smart charging. The black line here shows where it's 80% of the capacity. The yellow dotted line is like if somebody turns on an electric appliance that is not usually there, just as a peak, what happens? And the red line is where the actual fuse blows. So you see that it's very, very scarce in some areas if everybody's going to do like the average thing, charge at the average time. Then we need to do something. But if we change when the vehicle is charging, and this can just be done with smart charging, then we see that the load curve and the base load is beneath the threshold, and it's a suitable way of operating the household and the grid. This could, of course, be a adopted into a multi-unit dwelling, school, or whatever, but the case is the same. How can we make sure that we are using the energy at the right time while the customer is still getting the energy that they need? So I have taken the liberty to set up some load balance schemes for smart charging. What is the important part? So one of them is to actually respond as a passive asset, meaning reducing the amount of current going towards the charger when the grid has capacity issues, or if it's a low production, again, reducing the consumption to make sure that the EV is not the thing that is raising the prices. If it's an overproduction, we have the complete opposite side of the things. If the wind is blowing and the sun is shining, let's charge the EV as fast as possible so that the energy company can get as much money as possible for the excess capacity in power. And in Norway, again, the peak power, if we have an issue with peak power, then it's all about reducing the peak power behind the meter and ensuring that there's enough energy to the vehicles so they can operate in the way they're supposed to do at the right time. Then we come to the fun part, which I call vehicle to X or vehicle to grid. Because here we can actually use and utilize the battery as a resource in addition to the passive way of alternating the charging of the vehicles. So we can have the EV respond as a passive asset, which you can use it as a battery returning power to the grid. We can, again, if there's energy demand, we can, again, reducing the consumption or increasing it. And then we actually are helping the DSOs and TSOs serving their purpose, and we can sell this as flexibility. Or for the facility management, it's all about ensuring the lowest potential operational cost of serving all the different charging stations. And with the vehicle to grid, we can then transfer energy behind the meter, which has a very little to low cost, instead of adding extra battery storage inside the home. And of course, as the last option, an EV is a virtual power plant or a part of a flexibility pool. So anyone should be able to add this into an aggregator and make money of actually selling their spare capacity. So what is actually needed to do this? So for smart charging, UK has done some amazing legislations actually enforcing that every charger needs to be smart. If they can go one step ahead and make sure that everything has to be smart and on an open standard, then everybody could do smart charging. So that's simple, and it doesn't matter if it's AC or DC. So as long as you choose something that is actually open and hopefully has OCPP, then you can do smart charging. For vehicle to grid, there's a lot more that needs to be changed. For the first, the OEMs needs to support the feature. The charger needs to support the feature, and we have a long way to get the DSOs and TSOs allowing a new type of energy resource giving back to the grid that they don't control. Technically, it's already there, but it needs to be implemented in such a way that is actually feasible. So that is the challenge that we see today. And in Norway, we are working with multiple units that is fixing this every day. And soon we hope that we can also show that this is possible with something else than just a demo. So CCS will come soon, which at least most of the superchargers and small chargers in Europe supports now. So that's it for me. Thank you very much. Looking forward to any questions.
Yeah, thank you, Åsmund. Yeah, thanks for that insight from Norway. That was really useful. So to the audience of this session, please do remember to type your questions into the chat box, and then we'll catch them when all four speakers have finished. So next up, we've got Valts Grintals from UK company Kaluza. Kaluza is an intelligent energy platform that introduces new flexibility into the energy system by optimizing individual devices. So welcome, Valts. The virtual stage is yours.
Thank you. Hey, everyone. Yeah, my name is Valts, and as previously mentioned, I work for a company called Kaluza. And today I'll be talking about our domestic vehicle-to-grid trial that we've been running in the UK. But firstly, I'll just quickly give an introduction of the company, and then I'll focus specifically on the optimization that we managed. And after me, you'll hear more from Ben around the actual technology used or the hardware used in this trial. So Kaluza is a platform solution that basically offers different energy supply capabilities out of the box. It's a solution that SaaS solution being sold to retailers, has different components that offer different services to these retailers. But the two main components are Kaluza retail component, which is the tool to transform energy retailer experience and increase their operational efficiency at lower cost and empower customers with more data-driven, more energy insight-driven product. And then there's the Flex tool, which I'll talk more about later, but it's basically the intelligent platform side that connects customers and their devices to the energy system by intelligently managing different devices in customers' homes, including vehicle-to-grid. Here is a bit more detailed picture of what the platform really does. So as I previously mentioned, we connect to different devices in homes, including vehicle-to-grid. It also includes storage heaters in customers' homes, heat pumps, home batteries, regular smart chargers as well. And what we do is we use this ability to communicate to the device and connect the device to integrate with different markets across the board, including wholesale market, distribution network operator markets, some more local flexibility markets, as well as the transmission system operator, and also local generation, carbon intensities, and other factors we take into account into the optimization algorithms that we have in place. I'm not going to take too much time on this because, as previously mentioned, this has been talked about fundamentally. Why is there a need for flexibility? Well, the system is integrating more and more renewable generation to kind of achieve net zero goal. So these are data points from the UK, but I think same applies to any market around the globe. You need more renewables in the grid. Renewables are quite intermittent resources. As you can see on the right side, more renewable capacity you have on the grid, there's more volatility in the market. This is expressed in imbalance prices in the UK. And with that volatility, obviously, you need a more dynamic demand to facilitate the generation. And that's where flexibility comes in. That's where things like vehicle-to-grid also come in. As for vehicle-to-grid, so the project I'm talking about here is the world's largest, the first and largest vehicle-to-grid project, especially on a residential scale. So this is a project called, I'm not going to pronounce it, sorry. I'm not going to try it, but it's a project where we worked with Ava Energy, Nissan, and Indra. We'll be talking later on in Senex, where we pulled together, where Indra built world's first domestic V2G device. We developed a web app and experience for customers, developed the customer proposition in the UK, which was customers who have this charging unit can get 30 pence per kilowatt hour export rate. So when they plug in and we use our optimization to export back into the grid, customers get paid. And we developed our intelligent platform capabilities to manage this optimization. This project has been running for 3 years now. There were 1,000 chargers manufactured as part of this. And within the Kaluza portfolio, we have 330 vehicle-to-grid devices in our customers' homes that we are optimizing continually. As for the actual optimization, you can see a representation of that here. So our core optimization for the platform in the UK is based around half-hourly electricity prices. And here you see a portfolio of 120 vehicle-to-grid devices operating. So you can see the orange dotted line is the electricity price, and you can see kind of lighter shade of blue being the export from the portfolio, and you can see the darker shade of blue being the import from the portfolio. So fundamentally, what the devices are doing here, they are, when you look at the prices are high, so the devices are exporting back into the grid because it indicates that there is a, I guess there's a need for additional capacity on the grid. It also, it gives us the ability to sell electricity at high prices back to the grid, and then we charge those devices back up overnight at lower prices, which helps us create a wholesale arbitrage value. So in this case, creating around £180 in one day from these 120 devices, saving 64 kilograms of CO2 while doing that. And this is even more valuable than a regular smart charging. As you can see, there's a 45% increase in CO2 saving when compared to regular smart charging. Here's another interesting example from specifically lockdown. So you can see the value of vehicle to grid in this specifically. So in the picture here, you see at the top is the percentage of renewable generation in the UK mix. This is throughout a day during lockdown last year. The second chart shows the system imbalance to which we respond. And here you see our portfolio charging patterns, and you can see that the portfolio reacts exactly to this. So during the high renewable generation period, the vehicle-to-grid devices charge up as much as possible. As soon as you get reduction in the renewable generation of the system, and you see imbalance prices and system imbalance spike, we export that green electricity back into the grid, delivering much needed capacity during these price volatility. And it's just a clear example of how vehicle to grid really delivers value to the system through our optimization. On top of this, we have also used vehicle to grid devices to respond to local constraint signals. So a local DNO sending us a signal telling us that there's a certain capacity requirement in a certain region. So we've done that, but our core optimization is very much based on a whole system situation. Just quickly to go through some key benefits at the end. So customers save up to around £820 per year through the proposition that we offer with this optimization, which gives customers around 3 million free miles. And we get around 16 gigawatts of daily, the potential we see from vehicle to grid in the UK is that you could get 16 gigawatts of daily flexible capacity by 2030, if obviously the previously mentioned technical constraints are resolved and there are more V2G compatible EVs and charging protocols. And based on modeling we've done with our partners OVO Energy, we also see that this could bring to the UK electricity system 3.5 billion per year cost saving on grid infrastructure reinforcement, basically creating a cheaper net zero future. And that's everything from my side.
Brilliant, thanks, Valts. Yeah, there's lots of information to convey from the Skirius project. So yeah, thanks for giving us the highlights. Yeah, well, I think that's how you pronounce it. That's how I pronounce it anyway. But there is quite a lot of information online, is there not, around Skirius in terms of kind of the benefits and...
Yes, exactly. I'm happy to answer some more specific questions here, but also there are materials, there are reports that people can read if they want to, yeah.
Yeah, brilliant. Thank you. Okay, so next up, we're going to hear from Ben. Ben works for a company called Indra, also based in the UK. So Indra were also part of the Skirius project. They manufacture and install smart EV chargers for commercial locations and home charging. So over to you, Ben. The virtual stage is yours.
Great. Thanks, Neale, and good afternoon, everyone. So following on from where Valts was talking about Skirius and the project we ran, Indra, as he mentioned, provided the hardware and some of the support for the optimization services for that project. So we'll talk a bit about that and a bit about some work we've done since the Sciras trial concluded. So a bit about Indra. We're located in Malvern in the UK. There's some snapshots there of our facility. I'll gloss over these, but happy to talk more about this with any of you later. Sciras, our part of Sciras was to develop and deploy the V2G chargers really in a domestic setting. So that's what made Sciras interesting from our perspective, was developing a V2G hardware and optimization that would suit residential customers rather than commercial sites. We wanted to increase the maturity of the products available, get data on how they were used and the impact on the grid, and then explore further use cases in which V2G can play a role. I think we were very much of the view that it's a case of when, not if, for V2G, but we needed to understand more about the technology, the role it would play, or where it would fit in the future. So, as I said, we focused on the V2G hardware. When we started the project, the units were fairly large. There's a photograph there of some V2G units craned into position on a concrete block or pad, costing £15,000 plus per unit. By the time we developed our unit, which is in the bottom left there, one person could fit the unit in pretty much the same manner as a normal domestic charger, with a unit cost less than £2,500, so less than a sixth of the cost of the units a couple of years before when we started. If we look a bit further about the unit, so it's really designed, as I mentioned, for residential settings, so up to 7.5 kilowatts. It's smartly controlled, and Valts has already talked about the Kaluza system that controls the units on this trial to make sure that we're importing and exporting at the right times. And it's the first bidirectional domestic charging solution of this type that's available. Fully CHAdeMO certified and Nissan approved. So we've got a few hundred of these units, both through the trial, but through some other projects and commercial opportunities we've been looking at as well. So building up a really good body of data on how these actually perform in the real world, and really encouraged as that we're starting to see some real interest from people in getting this sort of equipment installed. There's certainly a growing understanding that this technology exists, and people are really keen to start buying into it. So we're seeing lots of interest. In terms of the development of the hardware, I wanted to touch just a little bit more on how we achieved the sort of improvements I've just been talking about. And there were a few things that we did. So a lot of the focus was on the power electronics module. Obviously, this is the big difference from vehicle to grid and smart charging, where an AC system doesn't need the inverter. Clearly, a DC system needs to go from AC to DC inside the box rather than inside the car. So you can see the rather large inverter at the top of the unit there on the right-hand side, together with control electronics and DC contactors. Essentially, the AC comes in on the right-hand side through the inverter, and DC leaves on the left-hand side, or comes back in, depending if the unit's importing or exporting. So a move to silicon carbide architecture and power electronics, we've really been able to push forward what's possible. And for us, the future there looks like cheaper, more miniaturized power electronics to make these units more affordable and more easily deployable. They're still quite a bit larger than conventional chargers, as you've seen from the earlier photograph. We put quite some effort into how to get these manufacturable, and again, there's more work to be done. We built 1,000 of these under the initial Sciras trial. Clearly, that number needs to get up to tens of thousands and hundreds of thousands. So think about how we can make them more manufacturable. It is really worth us exploring as well. We did quite a bit of work looking at how best to work around some of the DNO challenges, getting approval to install V2G systems. So we've been through that a few hundred times now and have a good understanding of how that works. And it's fair to say there was some challenges there, but I think we found it getting easier as we went through the project, and DNOs became more familiar with V2G and what we were trying to do. So I've talked a bit about some of these challenges. We certainly found going through CHAdeMO certification, Nissan certification, was a complex process, certainly time consuming, but one that actually CHAdeMO is a good standard, especially compared with some of the AC standards, where there's a really lockdown standard, and so very well defined what we had to do and meet. It just took some work to make sure we were meeting the standard in its entirety. Challenges with the DNOs and really different levels of understanding of V2G and how it would fit, and the level of certification or testing that was necessary to get these things installed. UK grid codes changed midway through the project, so from G59 or 83 to 98, 99, and 100, which came with some additional challenges, particularly around G100. Install regs changed in the middle of the project as well, which had an impact on us. The introduction of the 18th edition install regs in the UK, which brought particularly some DC fault current detection requirements and a few other things around earthing that made things more difficult. And the integration with different vehicles and with Kaluza on the other side, and making sure that we really understood how different vehicles would behave, and working with Valts and the team at Kaluza around how to optimize the devices best. There was quite a bit to it, but pleased to say we had a few hundred units rolled out on that program, and it's been really successful in driving our understanding of the hardware and our collective understanding of how V2G can play a role over the coming years. I'll skip over the findings because I think Valts shared some pretty good data on these. We're largely seeing what we'd expect: exporting when the price is high and importing when it's low, supporting grid carbon intensity. We then moved on to a project looking at CCS. So we were really keen and remain keen to get into CCS-based V2G. Obviously, there's some challenges with the standard and the -20 element not yet being published, which covers bidirectional charging. But we developed, and you can see here the photographs showing one of our CHAdeMO units converted essentially to operate on CCS instead. And we successfully trialed that here in our lab, both with a vehicle simulator that we built and also with a VW ID3 that we were able to get exporting. Still a bit of work to do, clearly, before the technology becomes commercializable. We need the standard out. We need vehicle OEMs to buy into it. Some of the things that have been mentioned by previous speakers, but there's certainly a strong interest that we found. And we've learned a few things on V2G. So CCS and CHAdeMO are very different standards. CHAdeMO far more restrictive, but in a good way. That we and the vehicle OEMs know what we need to do to make things work. CCS we found to be slightly more open to interpretation. So I think we'll see more challenges of that type as we work to bring a product to market. CCS as an approach uses power line comms technology, which introduced challenges over noise, particularly at high power. And it'll be interesting to see how we overcome that in the future. The range of CCS controllers on the market, which is something we need to see improve. I think that will come as CCS V2G becomes more popular. However, we did find that fundamentally points 4 and 5 there, V2X, the benefits are the same, whether it's CHAdeMO or CCS, and vehicle OEMs are keen to support it. DNOs, utilities are keen to support it. We need to see the standard, particularly CCS, get up to scratch and publish the -20 elements, so we can really start pushing the technology forward and out to the mainstream and get vehicles that use this technology there.
Brilliant, thanks, Ben.
Thank you.
Yeah, so you mentioned 2 points that I was pretty sure would come up in the Q&A session afterwards. So that's the cost of chargers and how do we continue to reduce the cost of vehicle-to-grid chargers, and also kind of CCS as well, and how do we increase the number of vehicles that are on that platform. So maybe we'll come back to those questions in the Q&A in a session in a few minutes. So thank you for that. Our last speaker is Jesper Björkman, a Business Development and Partnerships Manager at Krafthem from Sweden. So Krafthem is a startup that aggregates many small resources, such as electric vehicles and other energy assets, to provide ancillary services to the Swedish TSO. So welcome, Jesper. The virtual floor is yours.
Thanks, Neale. Yeah, so as Neale said, my name is Jesper Björkman, Head of Business Development and Partnerships here at Krafthem, and we develop and operate a virtual power plant to enable aggregation and flexibility from clean energy assets. And as many of the speakers before me mentioned, with the energy transition going on and the addition of renewable energy, we see an increase in disturbances and also an increase in costs of countermeasures to actually balance the grid, which is the cost for TSO as of now. And what we do with our virtual power plant and how we define flexibility is both on the supply and demand side, because we both work with supply and demand sides. So we can actually regulate consumption or production, depending on what the grid needs. And some of our current projects as of right now is, as you mentioned, EV chargers, but we also work with a lot of small and large scale batteries. We work with some small scale hydropower plants and wind and solar farms as well, in order to provide flexibility from these new sources by sometimes actually reducing the production, so using curtailment to help with imbalances in the grid and to help with frequency regulation on the supply side, and for EV chargers, which I'm going to talk more about. And for batteries, we mostly work with reducing the consumption from grid, so help restoring frequency back to 50 hertz, which we have here in Sweden. So what I'm here to talk mostly about today, what we are actually doing today with a portfolio of EV chargers, is that we are active in the TSO national market here for frequency regulation. And we are active in one of the fastest markets here, which is the frequency containment reserve for disturbances. And here we have aggregated a portfolio of EV chargers to actually help with frequency regulation during times of disturbances. And the minimum bid here is 100 kilowatts, which means you need about 200 to 300 chargers to actually be able to provide the service to the Swedish TSO. This picture you can see here is a portfolio of, I think, around 2,500 chargers. And with that portfolio, we're peaking at about 1.6 megawatts, which you can see in the right-hand side of the graph. And this also, the blue line you can see is how the consumption from the EVs, or how the power actually varies during the day, which I believe most of you watching here are familiar. But it is a clear sign that most of the charging is done at night, and then the curve starts to slow down and go down to right before 5, 6 a.m. when people start to wake up and most of the cars are actually fully charged. But what we do here is we use machine learning algorithms to do a prognosis of how much peak power we have in the coming 2 days, because when we work with the TSO as of today, we have to be able to provide with 100% certainty how much power we can actually reduce, so how much power we can provide to the ancillary service market. So we place that bid 2 days ahead. And as you can see here, the green graph is our prognosis of what we thought we were going to be able to supply in forms of kilowatts, and they are also placed in blocks of 100. So if we're barely reaching the peak, or if we don't believe that we can provide a full 100 kilowatts, then we will always reduce that, or remove that block, so to say. A couple of the really tough points here, or like the tough technical requirements for this market and for this fast market, is that we need to be able to provide real-time data, which is 1 second data, which I think most of the EV companies and CPOs, they're used to providing maybe like hourly data, sometimes minutes, but we need to be able to work with second data, because we are actually demanded to respond to a frequency deviation in the Swedish grid of within 5 seconds. So in order to do that, we need to know how much power we are able to actually provide to the grid. And I should also point out that when we are working with this market today, this is not a vehicle to grid solution. It will definitely be part of our VPP portfolio in the future. But what we do here is we actually only pause the charging. And practically what this means for each charger is that we will pause the charging around 10 seconds in average, and 10 times per year. So that's a total of 100 seconds per year that we will actually pause the charging, because this market that we are selling our flexibility to is sort of an insurance market, and that's there for disturbances. So the actual, we tend to say that we don't affect the charging experience at all. So we let our users or this portfolio, the chargers, they can behave any way they want, and then we will adapt to how they are behaving in order to place our bids and help out with frequency regulation to the grid. So yeah, you can see here, peak is about 1.6 megawatts, and we can see the potential because this was around 2,500 chargers, and the peak power was about 1.6 megawatt. So with an increase in EVs in Sweden, we see that there is a potential for about 1 gigawatt peak of flexibility for ancillary services, and also for local flexibility markets, which is something we are looking into now. But those sandbox markets here in Sweden are still very young, and the potential for 2030 should be around 2,000 megawatts. But yeah, we see an increase in demand and an increase in inquiries from various different manufacturers and customers wanting to help out with this. So yeah, the next step from here is just adding new types of EV chargers to our VPP portfolio. And yeah, also continue to grow our VPP portfolio with our other assets in the batteries and other production sites. And also we're working with a lot of ongoing projects on the heavy EV side, such as EV bus depots, which usually can provide around 1 to 3 megawatts of flexibility. But yeah, I think that was all for me.
Okay, great. Thanks, Jesper. That was a really interesting snapshot into the opportunity from the Swedish point of view. So thank you. Great. Okay, can the other speakers join me back on the virtual stage, and we'll move into the Q&A. Great. We seem to have gathered an extra speaker.
Perfect.
So I'll just wait for him for Frode. Is that how you pronounce it? All right, he's gone. Brilliant. Okay, so thank you again, speakers. That was really interesting. We've had one question come through in the chat box so far around battery degradation. So we'll come to that in a second. We have only got sort of 7 minutes or so until we need to break for the next break. So I'm going to borrow a question that I've seen in an earlier session and ask each of the panelists this one hopefully simple question, but probably a long answer, but try and keep it short. So if you had a magic wand to solve one problem when it comes to vehicle to grid, what would you use your magic wand to solve? Åsmund, can I come to you first?
Yeah, I'll say standardization.
Standardization.
And it means basically software, hardware, and vehicle needs to follow the same standard.
Yeah, and we could talk several hours about standards. Okay, thank you very much. Ben, what would you use your magic wand for?
Can I use it for the same thing? I completely agree. Standards, particularly, I mean, having multiple DC charging standards is just a pain. Having a single standard, particularly for vehicle to charger, would be a real help. So yeah, I've got to say the same thing. It's the single biggest thing we could do in my mind.
Great. Okay, thank you. Valts?
Yeah, I'll say the thing that I think will trigger standardization, which is I'll make all EV OEMs get on board the vehicle to grid. Once they get on board, I think it's all sorted. So that's what I would do.
Yeah. So yeah. Okay. So if there are any German OEMs dialed into the session, take note of that point, please. And Jesper, what would be your thing you'd solve?
Well, if the wand is magical, then I would want to see more policy incentives and the need for like a system perspective from the OEMs that we need to make each asset, no matter EV or battery or solar panels, that we need to think of the resource efficiency of every asset that we are adding to the energy transition to help reducing the CO2 emissions. So actually putting an incentive or putting the demand on the companies and OEMs that are actually providing the assets or EVs, or yeah.
Yeah, great. Okay, yeah, thank you. That was really insightful to see. One sort of other general question I had, and I don't think it was covered too much in the presentations, is around kind of consumer uptake. So both residential vehicle owners and EV fleets. Do they understand vehicle to grid? Do they get it? Most people are still grappling with how on earth do I charge my electric vehicle, and then obviously vehicle to grid is another complexity on top of that. But what else can be done to make sure that the proposition to customers, whether it's residential customers or EV owners, is as compelling as it can be? Åsmund, I'll come to you first.
Yeah, I'll just jump in. People as you say, struggling already to even charge, and lots of energy companies doesn't understand flexibility of virtual power plants. So then we have only one incentive left. What's in it for me? So does the economical gain the customer gets, is it higher than the cost of actually reducing the efficiency of their charger? If the answer is yes, they will come. As of now, they're still scared, so they won't. But once everything starts to actually work the way they think, then if they can make money, they will come. So I'll just say that nobody in Norway drives EV because it's green. We drive it because it's cheaper and it's really nice that it's green.
Yeah. Okay. Thank you. And Jesper, the sort of view from Sweden. Do consumers understand vehicle to grid? Do they get it? Or is it still too new?
No, definitely still too new. And I think what we need to do is just educate, simplify, and also work with guarantees and just. I mean, what we're doing is not V2G per se, since we're only pausing the charging, which won't affect the cycling of the batteries, etc. But even with V2G coming to Sweden as well, I think we need to just simplify more and also see more guarantees and to be able to answer the questions or the worrying that will come from the consumer side.
Yeah. Okay, thank you. So one eye on time, we had a question on battery degradation. So Ben, I know you were going to offer a response on that, but just to add before you do that, one of the other vehicle to grid projects from the UK is actually looking at battery degradation as part of its real world demonstrator phase. So the University of Warwick within that project is actually due to publish a paper on battery degradation sometime spring next year, March, April time next year, which will kind of add further evidence to the whole question of does vehicle to grid degrade or not degrade your battery when you do vehicle to grid. But Ben, you wanted to summarize what we know at the moment.
Yeah, sure. I mean, at risk now of contradicting whatever Warwick say in a few months and looking silly, the evidence we've seen from our trialists is that there's no adverse effects, particularly from V2G. Certainly no more than driving the vehicle. So sure, you're putting additional cycles onto the battery, which is one of the things that causes batteries to degrade over time. But you're doing it between controlled state of charge thresholds, so you're not doing it at particularly high or particularly low states of charge, which causes that degradation to occur faster. You're also swapping time sat on a driveway or in a parking space with a full or nearly full battery for time cycling, which we find in some cases, there's a few examples where it's improved battery health. Yeah. For the majority, they've seen really no adverse effects. And I think I think we're too used to really old batteries where you use them too much between too narrow a percentage band and we just see the things drop off a cliff. It's just not where we are with modern car batteries. We're just not seeing that sort of performance. And I would expect, I'd be very surprised if the Warwick study doesn't reinforce that point. There'll always be the odd outlier for whom their experience is slightly different. But no, in the main, it's really not a point of concern. It's another part of the education piece that we need to get across to people. Really,
it is. Yeah, I mean that confirms what I thought the latest was in terms of a little bit in, a little bit out, a little bit in, a little bit out is actually potentially positive for the battery overall, rather than it trashing the battery, which is, if you're a Joe Public, you might think, why on earth would I do this? Why on earth would I ruin my new EV batteries by using vehicle to grid? That isn't the case. Brilliant, thank you. And then we've had one other question come through. I think, Valts, you're well placed to answer this, because it sounds to me like a question around the remuneration to a typical customer who does vehicle to grid. And I know the Skirius project had some findings on that. So the actual question is, how much would it be worth to sell a kilowatt hour from a car? And I guess the answer to that is it depends, doesn't it? There's no single answer. It depends. But what did you find from the Skirius project for a typical user?
So I guess you can see the reflection of that in the tariff, the proposition tariff. So customers get 30 pence per kilowatt hour of export, which is, it's quite generous, but this is extracted from learnings operating in a imbalance or optimizing against imbalance prices in the UK market, basically. So it will differ depending on seasons. It will different depending on events. We're doing analysis just now of how the recent gas prices have affected the value of vehicle to grid. It has either seasonal and their event-based impacts, but the average figure that we come up with is 30 pence at this point. Obviously, the more markets become available, you can add to that. And this is just purely based on wholesale. So there's definitely more that could be done, and you could get more per kilowatt hour. But at this point, it's, the figure we come up with is 30 pence per kilowatt hour.
Great, thank you. Okay. We'll have to end it there, although I'm sure we could have talked for a lot longer on this topic. So thanks again to the speakers. That was really interesting. Thanks for your time this afternoon, and thanks to the audience for. So we're going to take a 7-minute break and restart at 2 p.m. UK time, 3 p.m. for our colleagues in Europe. So the next session is around wireless charging solutions. So we look forward to seeing you in a few minutes. Thanks ever so much.